This is just a supplemental video to go over some dimensional analysis. So I know it might be a little confusing or maybe it bugs some people to see. Of course, we know that our force is typically reported in newtons, but in the previous equations we're using, we're plugging in coulombs and farads per meter and meters. So how does that give us newtons? And so that's what I hope to show here. So going back to our equation for force that we had earlier, dimensionally, so we know in the numerator we have Q1 and Q2, so those are going to have dimensions of coulombs, so C and C. We then have some position vector, which is in units of meters. In the denominator, we have that epsilon naught, our permittivity of free space, which we have in farads per meter. And then we have the magnitude of the distance cubed, so that would be meters cubed. Okay, so we can straight away start crossing out some of our meters. So we can say that these two are going to cancel out with two of these, so we're left with just 1 meter in the denominator. And now we want to relate this farad to sort of some more basic units. And so we can do that with our basic equation Q equals CV. So our charge is capacitance times voltage. So we can rearrange and solve for our capacitance, which is equal to Q over V. And so what that tells us then is that dimensionally we have farads for capacitance, which is equal to coulombs divided by volts. So now I'm going to take that and plug that in place of my farads here. So I can say that my force is equal to dimensionally. So again, we have these 2 coulombs in the numerator, so I'm going to say that's coulomb squared. And now we're going to replace this farad with a coulomb per volt, and we still have the meter over here. And so of course we see we have one of these coulombs in the numerator canceling out here, and so what we're left with then is coulomb volt per meter. And so here what we can do is we can think back to when we introduced our electric field intensity, and we said that it can be reported in Newton per Coulomb, or more commonly we'll use volt per meter. So rearranging this a little bit, what we can do is we can solve for our volt. So we can say a volt dimensionally is equal to a Newton meter per Coulomb. So now we just want to substitute that expression in here. And so, we can think of it here. I've sort of simplified it a little bit there. So doing that, we get that our force is equal to, dimensionally, in the numerator we have the coulombs, and now in place of my volts, I'm going to substitute in my Newton meter per Coulomb, and we still have a meter in the denominator. And of course we can see our coulombs and our meters are going to cancel out, and we're just left with our newtons, which of course is what we knew to be true, but hopefully this gives you a little better understanding of how that works out in terms of the other units.